Hi, my name's Bob Grinier and I'm a volunteer with the Martin Fleischmann Memorial Project. So thank you for joining me here this 28th of April 2023 for Windhexe Update 2. This is an update for the end of the fourth week in April 2023. Yes, Rob, the sound works today. I think I finally fixed it from where I was in Japan recording the videos. Hopefully it'll be good from now on out. So how is everyone? Hi Gordon, hi Cosmic Dave, hi D2105K, Rob, hi Artifact and Corky Goss. Hi Terran Art. In answer to your question, Terran, Bobcat and Phil Power in Sweden and New Zealand respectively helped cover the cost. The van was quite sizable. It was difficult, but I think we'll be helping Lion's wife out very significantly in dealing with the material there and hopefully rescuing any experiments that Lion might have squirreled away. So I don't know what's going on with the screen. We've got the sound, I guess, but there's a little bit of a yellow cast. I think people are going to have to live with that today. Sorry for that, but that's as it is. And let's see. Hello. Right, so what have I got on the screen there? Well, this is part of a Finnish sword hilt. It's from the 3rd century, Anno Domini. And it obviously has these quad triskelion type vortices. And I don't know if you can see it, but from, say, for instance, this one on the right-hand side, it has a thing that comes off and goes into a 9 on this side, and then we have a 6 that comes out here and goes into the triskelion there. Again, we have it like here, and we have it like here. So I find this quite interesting because this is very similar, this 6 and 9, to the one that we have on the top of the Coptic Circle of Life, as I called it, Stella. And this is obviously in Finland, and it is contemporaneous with that of the Coptic Christians in Egypt. How can that be? And of course, we are saying we have the caduceus spiral, the sword, coming down from our Windhexe auspicious symbol, vortex structure. And of course, this is actually a sword hilt with just such a structure at the top of it. So it's a symbol of power in a tool of power projection, I guess, a weapon. But we can use things for good and for evil, can't we? So the saying goes. But I think it was a beautiful, beautiful thing. And just another one of these examples, how are they representing a technology they know? Is it just coming out of their attachment to the Akashic record? It's like it's science that's bleeding into their consciousness. You know, is it something that their predecessors knew, or did someone try to teach them it? Why do they do this? Or is it just pure art? What is it? Hi, Louis Navarro. Great to have you here. And hi, Ken Pratt. So yes, that is a 3rd century sword hilt in the museum in the capital of Finland. And there we go. So, talking about little miniature vortices, Chris Scott is up first in this review. And he has been building a Rankkielsch type vortex, sort of like a mini Windhexe, and you can see it over here on the right. And he is using a shop compressor to make his mini Windhexe. I think he's got a plastic funnel on there, a piece of Perspex with some type of bonding agent sticking it all together. And he is using an optional espresso machine steam injection, which I think is wonderful. Hi, Jouni Tuomela from Finland. I probably ruined your name, but I'm sorry. Yes, this is the Espresso Plus version of the miniature kind of Windhexe. Now, where I don't think this is a replication is that the hot moist air should be coming in at the same time, and actually where the steam is being injected here, that is actually in obviously the Windhexe. That should be the exit port. So anyway, it found some interesting things. The injection has a knife edge on it to make a whistle, and it's got half of the circumference poking out. So the injection nozzles effectively are at the same time the deflectors that you have in the Frank Polifka Windhexe patent. So there we go. Hi, Daniel Foster. Hi, Dan Moretti. And he has some notes on what was going on with this. He said, definitely some weird things happening with my induction meter. It seemed to stabilize at around 12 amps with air only, and went over limit and, in his words, drained the battery effect when I added the steam. When I checked the magnetic field on my phone, it was very large, in exactly the spot on the iron freezer where I had earlier put the ammeter down. Something to keep in mind, any coils in the vicinity of the Windhexe might see an electromagnetic phantom. Hi, Drive, Rajput, and hi, Donald Best. So he is recording some weird things going on, and you know the sort of electrostatic kind of charge dropping water, and there's all these discussions around the counter directional flux of moist air and the friction build up and the static charge build up. Well, anyway, he's seeing induction of quite sizable amounts, and there's a sequence of videos here which I will play. I hope the audio comes through. Let's see if it does. So here is the first of the videos. Let's see if it does. So at this point you can see the espresso machine, and this is the steam injection going in here. And essentially it would appear that the steam injection is going into the sort of Rankkielsch vortex type area with the auspicious symbol type injection of pressured air through the whistle. So it isn't quite a Windhexe, it's somewhere in between the two, but it's an interesting study all the same, and it just goes to show what you might be able to do directly with a compressor and using steam. So we'll go on. So you can see there he was getting about 7 amps or whatever and came up to about 9 amps. Now with the steam injection here, It's 10 amps. Getting on for 11 amps now. .5 amps. .12 amps. Yes, Simon, you should need at least 3. 2's not really good enough for these kind of things, but at least 3. That's in the patent. 13 amps. Okay, so Scotty is saying it's air up to this point. Well, okay. We got 14 amps. Hi, Scotty. Thanks for joining us. And you can see the steam coming out of the bottom there. 15.3 amps. You see the steam there. I wouldn't put my hand down there if I was anyone there. So David Bertilio's question is, was this on AC amps or DC amps? Can you answer that question, please, Scotty? Was it AC or DC? Actually, I can go back in the video, maybe. We can see what the setting is. It's on amps and, I don't know. Scotty, it's on DC amps. Okay. So thank you, Scotty, for that clarification there. Scotty, if you want to add any comments into the chat and I can read them out for people that are only able to see the video on various formats, that would be good. Anyway, I think this is a fascinating test. It brings a whole other dimension to what may be going on. I mean, obviously, with the amount of steam being injected here, this is quite a lot of humidity. So the next test here, Scott might like to clarify if there's anything particularly special about this. He's shining a light in, I guess, to see whether he can see any of the vortex going on. Now, are you shining a light up through the bottom? I think you probably are at that point there, or at least from the side, Scotty. Yeah, I can see you shining the light up from below. Scotty, what's the PSI? I can see the rated PSI on the pipes. So Donald, I believe he's got steam coming in from the cappuccino machine at the top, and it's coming out somewhere around about a little bit below the vortex that's for the shop compressor coming in. Well, I mean, Polygon's saying that steam does produce electrostatic charge for sure, and here we are. It's very clear that it does. So it's a very, very nice test. Hi, Elias Lionheart Graham, and hi, the Bippo 5. It's really nice, this test. So, and I do know that someone in the UK is doing a similar kind of test, but not with a cappuccino machine, at least not at the moment. Well, that would be interesting, Terranar. Is injecting a small amount of a Marsa gas might help. That would be very interesting, yes. Okay, so I think what you've got here is that 23.55 amps there? 24 amps, 26, 27, just before it 32, 32, and then it drops back down again. So in that frame there, I don't know if you can see the top left, we've got 32.59, so 32.6 amps. So I think that's an excellent series of tests there. Chris, thank you very, very much for sharing those and actually conducting them and playing around with steam and compressed air is always... Yeah, so David Boutillier is saying that maybe there's a strong enough magnetic field to be detected by the Hall effect sensors in the magnetic circuit, the meter, potentially. Scotty says, didn't get an exact PSI. I could guess at around 10. They're typically the shop compressors, something like 9.5 or something. Yeah, so it slowly built up ahead, so... had a continuous range. Okay. So David Butlier is saying that meter is not detecting amps. Well, that's kind of my feeling. We're not actually looped around anything, so something's going on. Okay, it's in detecting induced magnetism in the Hall sensors. Okay, so perhaps, Scotty, you can look at getting some Hall effect sensors. Obviously, you probably have them in your phone. And maybe that was detecting the same thing that's causing the supposed amps that you're observing here. I mean, if it was real amps, maybe you could have a loop and try and power an LED or something a little bit more interesting. But we do know that dropping water, for instance, produces or captures an electric charge. And the whole understanding in conventional terms about a weather system is that the friction between the sort of moving water and stuff is one of the ways in which charge is built up. At least that's what we're told. Okay. Yeah, it'd be interesting actually if, I mean, I don't know how many of these parts are iron and how, I think these look like they're aluminum. I don't know if there's any iron parts. Is it steel? Be interesting to see. Okay, so just to review, I think this was a non-steam test in this first one. So I think he said it stabilized at about 10 or something in that one. The next one was, I think it's got some, maybe this has got steam in it. No, yeah, this one's got steam, but not at this point. It's got 10 here, roughly, and then I think he throws in the steam. You can start to see it coming out the bottom. And there's the steam going in, and then it starts to rise quite quickly in terms of the whatever it is sensing it. And it gets quite steamy at the end here. You can see that coming right out there, and it goes up to quite a high degree. So, although this isn't, it's a more Rank-Hilsch vortex, it's kind of like a combination between the two, and we don't have the outflow at the top here. It's kind of a mashup, but it gives us a little sense of the potential for some kind of fields going on in these systems, and I think it's a very, very valuable experiment. So So Harry said, lots of laugh. How is there electricity if it's just spiraling air? Well, yeah. But, you know, that's something to think about. Yeah, an analog meter might be the way to go. And then you're not getting something confusing things. Right, so that's basically Chris Scott's test. He did note that his ammeter was a bit messed up afterwards. So next up is the tests of Henk Jurien. And as I said in the last presentation on the subject, he took the sacred geometry structure and developed a very simple cone and a half sphere and a cylinder to match with the geometry. Okay, and this one's quite a good guide, this image, which you can get off remoteview.icu, where you have both the Sothic triangle and the Frank Polivka Windhexe overlaid, so you can design it. Now, I think that it might be interesting for him to drill a hole the same kind of dimensions as the Polivka port and have something that can slide up and down in there. But already he's producing some very interesting results. So tests beyond what you've already seen in the last review is this one, where he has some mica supports and he put some neodymium-based high-strength magnets underneath. So it was supported in the center here to stop them falling down. And unlike what you observe ordinarily, where he says that ordinarily you just get this black sooty layer on the inside, what happened when he had the magnet here, there was actually these kind of Evo tracks going on, these discharge tracks. And in fact, on the magnet, here you can see they're kind of bleeding out from the magnet itself over to one side, but that's just, you know, but they are coming from the magnet, it would seem, or going to the magnet, one or the other. But on the magnets themselves, they're actually going around like they're annular. So you can actually see the track going around. And down here, it's kind of like, I actually don't know which end was attached to the metal dome, whether it's this end or the other end. But anyway, at this point, at least, it's practically going around in the horizontal. Now, this was the metal that was done in that experiment. And so you can see that he had mica supporting this. So you had the dome, you had the magnet. The magnets became demagnetized, and as I discussed with him, these neodymium magnets, they have a very low demagnetization temperature. I think it's like 50 or something, like 56 or 70 degrees or something. Offhand, I can't remember exactly. I said, you need really some samarium cobalt, but even then, they'll eventually go. But that being said, you can see here that down in the lower part, there was this large amount of the aluminium eaten away. And you can see the layers of the aluminium have been eaten through, but relatively untouched at the top. So I guess this experiment with the mica and with the magnets let him think, well, maybe I can do just something with just the mica. Okay. So he did this experiment with a piece of mica here with the dome on top. And again, on one side and towards the bottom, so you can see that this is a 1 centimeter mark. So these are 0.5 centimeter squares. It ate out a hole one side into the center. Okay. And what I've asked him to do is in future tests is, and this is the same for, and you'll see this in the work of Tony Jabony, Acc Robb, to see what happens when you align it with the cardinal points. Is this just some artifact of the environment within the local reactor, or is this something to do with the cardinal points? And that needs to be established. Anyway, so it was able to bore this hole out in the center, but almost entirely leave it untouched on the top and almost entirely untouched on most of the rest of the sides, just sort of coming in from the side. Okay, now he thought, well, okay, so we've taken away the magnets, we've just got the mica sheet and the dome. What happens if we take away the dome and just have the mica sheet and the mesh? Well, very, very different. So in this case, it kind of gets eaten all over on the outside. Okay, so in this case, we get a borehole to one side eating in, which is quite similar to this one, which had the magnet, remember? So we had the mica holding the magnets, and in this case, it produced this result coming in from one side, not very much touched on the top. I don't know how long this was in, but, you know, the longer you leave it, I guess, the more it consumes everything. This one was in long enough so that you just got the damage in this one point. But in the case of this experiment where you remove the dome, it seems to be more all over. Anyway, this needs to be replicated many times to see what happens. Okay, so I am going to go here. You see my ugly mug, and I'm going to bring up some of Tony's work in a second. But I don't know if Henk is in the chat, if he's managed to join us. Yes, Overwound Games. This was in his reactor. So essentially what Henk is trying to do is to replicate the kind of create the sacred geometry effect, because he already knew from his experiments before that the the plasma likes to hide, as he calls it, and this led effectively to creating the angled brass on the iron plate that led to the creation of the wormhole and the map of the Great Pyramid design. And so, you know, it's kind of like, well, then what happens if it's in this dome? And this is his inspiration, is to, you know, reduce the sacred geometry down to, you know, what might be the working minimum, and see if it has an effect. And so that's essentially what he did, and that whole thing is placed in his reactor and produced these various interesting results so far. The great thing about this experiment is it's very, very quick to do. And in fact, if you want to work out what the thing does first, you want it to be a quick experiment, and you want to stop it quickly, and then you want to repeat it. You want to see if this occurs every time with an orientation to the cardinal point. If it does, then that's an interesting finding. You want to see if this always does the same thing with the same time, same exposure, same pressure, same power input pulse. What he's having a problem doing right now is because it's extremely bright. And so I will be going there next Thursday with the alpha, and we'll hopefully be able to look into the plasma as these kind of events occur, and we'll get a better understanding of what the actual structure is that's forming and how it's burrowing in. Is it coming from the inside out, or is it going from the outside in? And these things are very useful to learn. Okay, so I'm going to go now and get some of Tony's excellent work. There's a lot to share. First off, he has a PDF of the experiments that he did, and there are many. And I have a directory of videos which we can look at, and then in the blog I will put all the links. I mean, they're all accessible anyway on the blog in the original Windhexe blog. And if you want to follow this directly as it happens, that's where I would encourage all experimenters to put their comments. And, you know, I will do periodic reviews. There'll definitely be a review at the end of next week when I have also, the plan is to visit Tony Jabony, aka Robb, at the same time as visiting Henk, and we'll do a bunch of experiments at both places. I'm kind of hoping that we can get a large, what do they call it? Air pump, the same thing that was used by Frank Polifka, because it produces. We can control the pressure and also have a continuous flow. But what Tony is doing already is fantastic, and he's doing it in such a way that it has to be commended. Really excellent work. So I don't know whether this is his latest one. He might have updated it since I pulled this off the Google Drive, but he's doing a whole series of tests. So you can see the most important thing to start before you do anything is coffee and clearing the workshop, and then setting up the Windhexe. And here it is, and it's a very beautiful thing that he has built. And we got checking the north-south alignment, because I asked him, this might be a parameter that may be important. It may be more important as the thing becomes more coherent or more stable, and maybe the intensity increases, but maybe it's not relevant. The leveling of the Windhexe, making sure the upper chamber is level and the exhaust is pointing straight to New Zealand, plumb. Setting up attaching the air compressors, one large shop compressor with a large buffer tank at 7.5 bar, 105 psi, and a small shop compressor at 7.5 bar, 105 psi. And he doesn't know how much cubic foot per minute this produces. The hose aperture is 6 millimeters in diameter, so that's probably a restriction on what can flow through it. Making a smaller exhaust aperture, and setting up a tripod and camera. And so he's done a very, very detailed set of what he's doing here, and then he's done these whole bunch of tests. Test 1, recording no material, just setting it up for a run for 1 minute. Recording of an aluminum can. Duct tape the sides of the inlet housing, felt air leaking through glue seams, so some issue there with some leaking. Test 3, recording aluminium can. So you can go and look at this. I'll give the links in the blog. I'm just going to go through first a bunch of images of the Windhexe after it was constructed, and then we'll go through some of these tests, and maybe Tony can jump in and make some commentary on that. So here we go. This is very, very nice work, Tony. Absolutely beautiful. So you can see the inlet port here with the seal, and you can see the snap-on fit for the gas under pressure. Here you can see the ready rods, and the ready rods adjust the height of the output duct. And you can see that these are coming in at an angle and coming in at an angle, and these are the ports. Here he is leveling it up, and if we go on, there's another shot of the leveling up here, and it's level, albeit within a fag paper. That is the beautiful device, and you can see down the bottom here he has got some alignment going on here, making sure he knows where it is aligned, and this may be very important. And he's got the south port here. Okay, and so there we go. There's the alignment. Here is the east side, and here is the temperature and the humidity, I guess, on an analog dial for those that like that. And here is a digital one showing 52% humidity, and it's 58 Fahrenheit. I guess is that 25 degrees centigrade? Maybe you can clarify that. I think it probably is. Okay. This is micrograms per meter cubed. Okay. And there we go. So number of particulates. So he's got the PM10 figures there. Number of micrograms per meter cubed. And so I guess what you're doing, Tony, I saw you with a very good face mask on, and really good and appropriate safety procedures. He had a face shield, breathing apparatus, and he had a what do you call it? Earplugs as well. Don't know if there's any issues with the YouTube stream. It's complaining that there's not enough data, but we'll see. So he's saying that some of the nasties in the air are safe. Okay, so this is good things to monitor. So yes, so Robb is confirming that he had hearing protection, full face shield, and dust filter on pressure. That's really good. This is just the way it should be done. Okay, so he's got this shim here or something that he used to, I guess, set the width of the whistles. And this is 0.64 of a millimeter. And so you can see here he's set the whistles here. And if I zoom in, you can see how you adjust by undoing this top screw and sliding this in and out so that the port for the air to go in changes its width. Okay. And here he's got a 1.21 millimeter shim to put in there to adjust the width. Okay, and you can see that this is a little bit wider, as one might expect as it's getting wider. Okay, and this is the overall assembly, so you can see it with the pressure hoses on there. And you can see the value of that Chinese device where it has a torus, and I know Tony is considering, or Robb is considering putting it on there. I guess it could fit underneath in this cone, and then you could have like one port going in, and as soon as you turn a valve, you could then simultaneously pressurize all ports at the same time. You'll see when I play the videos that it's a little less elegant, but he's making good progress already in terms of understanding what it can do. Okay, so it's a really, really beautiful thing. I like the way that, and this is just, I don't know whether it's his artistic sense, but he's got the cone coming down here and he's mirroring that to a degree up here. I think that's a lovely little bit of artistic sense going on there. Okay, so again, this is a piece of what do you call it? Not particle board. Oh God, it's just not shiplap. I don't know what. I can't remember what it is. It's shuttering ply, and he's using that to create the port at the top, and that's the south. And he's marked on here the width of the whistle slit for this test, and so on. So this is very good. And in fact, what he's done with the videos is excellent in terms of recording the data and burning it into the videos. This is a really good technique for ensuring that when you come back to these things in the future, you actually know what you're looking at with some degree of certainty. And what you're looking at here is down into the vessel, and these are particles of yeast, according to Tony, and you'll see those in the experiment later. But I think that's a rather nice shot. Okay, so I'm going to look at some of the videos now, and we'll go through them in turn, and maybe Tony can in the chat make a comment or two on what each one is. So we'll start with one. It's always a good place to start. So he's changing the whistle aperture here. I think he's sped it up. He's checking the shim there. So yes, Robb is saying adjusting the whistle slits to 0.4 of a millimeter. Excellent, excellent work. How to. And I guess you had to do this 4 times, right? Done. Lovely. So this is video 2. You see how he's burnt in the specifics on the left here. I know he's got them on this paper here in this logbook, but that's good too. So he's attaching manually the pressure hoses. So this is just a run for about a minute to see what happens. And I should probably move this bit at the bottom here because it's it's not where you want it. So the next one is recording aluminium can. You might like to add some details there, Rob, if there is any to add. Rob says there was no explosions or time warping or anything. I don't think there will, even if you had a lot of gas going in there. So the can gets lofted. The can gets lofted. So definitely once you put it in there, it's yeah, that's really, really excellent. Even at this stage, it's able to pick up the can. And eventually it falls out, I guess. So there's the can after it's been inside. A little bit damaged. And this is the can 2. So Rob is saying he doesn't almost doesn't have to throw it, like it's being pulled up. There we go. Not quite so good that time. Well, there we go. You hear it rattling around. I don't know whether it has to be perfectly level, Simon Claret, but he did that, you know, and I think it's a good thing to do. Okay, so next up is aluminium can. Sorry, this is recording exhaust. Sorry, no, aluminium can 3. This is larger exhaust aperture. So at the top, you can adjust the exhaust aperture, and that'll give you a different kind of dynamic. So it still gets picked up. So he's feeling where the air's coming out, and Tony said that the air is coming out one side. And there we go. Turn off the power. The can drops out. Have a look at the can. It's not looking too healthy. I have no sponsorship agreement with Fanta. Okay, so the next test I think is really good. There's 2 of these tests, and it's quite... obviously, there's many things that you guys are going to think up that need to be tested. But he's making huge progress on the easy wins, and due credit for him. The next 2 tests are smoke tests. It's not immediately clear. Maybe there needs to be some black card in the background and a light shining. That might be something that needs to be done, but you'll see, and maybe Tony can comment on it. Maybe Rob can comment on it. Is that a cigar, Rob? Oh, I think it's... I don't know. It looks like a very squashed cigar. Have you been picking up fag ends? Oh, it's a fungus. Horsehoof fungus. Alright, so he's seeing there's a jet of air coming out there because it's illuminating. It's causing it to burn a little bit stronger. You know I really like all types of mushroom and fungus, Rob. The idea of burning fungus. You know what might be good actually, Rob, is could you get like I don't know, some like could you get some like streamers or something? And tie them onto a wire mesh, so that you have loads of little like pieces of tinsel. Okay, like tinsel's easy to loft, and if you put them onto the intersections of pieces of wire on a chicken mesh, for instance, on a grid, you could then hold it under there, and you could see where the air is going in and where the air is going to the side, something like that. I think that might be a really good idea to give you a visual overview. And then you just cut them to the right length. Okay, so this is smoke test 2. That really is smoking good there. Excellent, excellent test, Rob. So Rob said that the particulate meter is going nuts on these tests. Of course it is, yes. Yeah, it's like when you're blowing a blacksmith's furnace. There's air blowing onto it, so the ember glows brighter. Okay, so this is a bunch of really fun tests, and you know, you can see that Rob is really having fun here. So the first is a handful of pistachios. Oh, so a couple are coming out. Are they whole pistachios or pistachio shells, Rob? Because, honestly, if I was doing the test, I would have eaten the pistachios first. Whole pistachios. Criminal. Criminal. Okay. So this is a handful of plastic wall plugs. You know what you should have done? Those little, like, packing beans. That'd never come down. You wanted them peeled. Oh, okay. Oh, look at that. It gets more ridiculous. You wait. You wait. He's done some great tests. Okay. It starts to get really fun now. Really fun. This is... Wait for it. Wait for that to end. Handful of nutritious... nutritional... Sorry. It's too funny. Handful of nutritional yeast flakes. Oh, you can definitely see it coming out in a direction there. See? Still great test. Love it. Love it. Okay, so the next one is nutritional yeast flakes close up. As if that wasn't good enough for you. Here we go. Nutritional yeast flakes close up. Yeah, I can smell it. I can smell it right now. The whole room would smell like farts. He's trying to clean it out, and I think cleaning it out gave him some inspiration for the next test, which is a sound analysis. And by the way, Rob, I'm going to bring this 384 kilohertz mic so we can do a very broad spectrum analysis of the sound. So I'll bring that with me next Thursday, Friday. Okay, so back in the room. Tom. I can imagine the drummers of Japan having a go at this. I think that's a wonderful test. I like it a lot. Right, so next one up is a semi-wet sponge. It fell out there. It did not dry the sponge. No. I do think we're going to have higher rates of flow. And I think we're going to have longer time to get it stable. And I think it's probably going to need to be higher temperature as well. Okay, so here is an apple. I think the full description is an old apple, because yeah. Okay, here goes. An apple. It stays up there for a little bit. I think the conclusion is we need some extra airflow for that to do anything useful. Gravity won that one. Yeah, apple still looks like apple. So, aluminium can with a new whistle value. So the whistle value here is at 1.2 millimeters. Or smaller apples. Yeah, crab apples. Let's put crab apples in there. So Jack, the original Windhexe is using a blower, an air blower, and maybe I'll show you the kind of one that could be considered. Yeah, industrial air blowers. Ooh, it's looking a bit beaten up there. Yeah, I think you need a combination of cubic foot per minute and pressure, back pressure on it. So this is aluminium can with a new exhaust height. So you see the exhaust height here is 122 millimeters now. I think it needs more heat rather than cool. So in the next experiment, he's varying the outlet aperture. So this is the port at the top, rather than the exhaust height. It's the aperture on the top. So here we go. The original used a blower and a heat exchanger in between to control the temperature of the gas coming in. So, of course, the problem with using an air compressor is that the air coming out is actually likely to be colder than ambient. So, for instance, the functional test with producing dried powdered sweet potato in the, I think, 2006, 2005 experiments that were done in America, they used 110 degree gas coming in and above. I don't know. Have you, Rob, have you measured the temperature of the gas that's coming out of the air compressors? Because I think it is a very important factor. Chris Scott thinks it is possibly the most important factor, the temperature differential. Did you measure the temperature of the what do you call it? Well, no, steam can go a lot higher than 100 degrees. Yeah, the water and steam coming out of a pressure cooker in your house can be 110 degrees. So yeah, it depends on the pressure, doesn't it? So of course it loses temperature when decompressing. But have you measured the temperature that comes out? Because ideally, what we're looking for is something over 100 degrees, and I guess probably it's the air going in is lower than ambient temperature. Okay. Yeah, okay. So, well, I mean, yeah, there will be some temperature differentials in the vortex in there in the structure, of course. Yes. Yeah. Okay. So, this next one I think is wonderful. It's looking for yeast swirl pattern. Of course, the tinsel on a grid mesh may provide the same thing without flying out in all directions. I would like to do the tinsel grid mesh and the yeast, and I'm willing to take the smell when I'm with you, Rob, with high speed, high spatial resolution videography, and so that we can study, particle movements and have a good idea of what they're doing. So, but I like this. But it would be interesting to see if, say, for instance, with tinsel, we can capture it kind of like in freeze frame, as it were, as it's working. Okay, so the next one is another test similar to this one. Really nice, this one. So D2105K says, was there an iron filings test? Okay, the next one is aluminum can changed exhaust height. So here you can see the exhaust here is 122 millimeters. On this one, it is 142 millimeters. Glitter is evil. No one do a glitter test. There we go. I don't know if it's the same can you keep using. It probably is. So here we got 2 half cans. There's no description as to how they became half cans, but here we go. We still got the exhaust at 142mm. Oh, okay. Someone says, is Fanta, as in fan. So I want everyone to give a big hand to the experimenters this week. Chris, Scott in Australia, doing kind of Steam and Rank-Hirsch Vortex type mashup with the Windhexe miniature and seeing potentially some maybe Hall effect or current things going on. So excellent work there. Some excellent work by Henk Jurien, and in the plasma setting, focused on the sacred geometry and using the single isotopic aluminum and see if that has some interesting effect. Really interesting things being observed already there in another fast cycling experiment. And big hand to Robb for this sterling build of this device. Really full on clap, guys. Really excellent work with this. Let's see these images here. Just really a thing of great beauty. And yeah, I think the major thing that needs to vary is to get hot air in there and a higher flow rate. And I think he's all over that. If I can help make that happen, or people can help make that happen before next week, then I'll be very excited. But it's already lofting things. It's already producing this vortex. It has this bit that comes out that Frank Polivka observed, but also this ability to loft things in there as well. So what we're learning through this process across the different experimenters is how this overall sacred geometry, this auspicious type structure works. And it's at a very gentle level. And when you had, say, for instance, one that is this size, and you build one that's bigger and you build ones that's smaller, you could maybe get an appreciation for the speed of what is going on when it gets smaller and smaller, and the moment that may be required to get it to do certain things. Now, I do believe that if you're able to increase the charge in there, maybe by ionizing it in some way, you could potentially have passive ionization in there. You could line the top surface, maybe, I don't know, or something in there with something that would cause ionization, maybe even some granite, I don't know. But if you had ionization in there, you will get charge separation, you will get charge clusters forming, and I believe the effect would get higher. But I think it's just perfect what the experimenters are doing baby steps, one step at a time. We know that it can rip apart tungsten. We know that it can rip apart alumina. We know that it can rip apart silicon dioxide. We know that it can tear through copper. We know that it can do all these things. We also know that in the level of the Windhexe, it is used for making dried milk. It is used for making dried powders of various things. And we know that if you get it right, you can start smashing up rocks. And so it's about finding the right parameter space. Now, with regard to the blowers, let me see if I can dig that up. And if people are going to chat, that's great. If there's questions in there, Robb's in the chat, Scotty's in the chat, they can discuss their... so Scotty's saying he's going to try and do a 2 kilovolt DC test next. And... Robb is discussing the paint that needs to go on the outside before this becomes a rusty hunk of junk. Okay, so just give me a second. I'll see if I can find this blower. So there's a real opportunity here for people to get their thinking caps on and propose simple, well-defined tests that can be conducted across the experimenters with these various implementations and concepts that they're using as test platforms, where we can learn. So, you know, it's often unexpected what you may learn from a proposed test. But sometimes you can, you know, say, I want to do this because I expect potentially, I hypothesize that this outcome will come out of this test. So it's really an opportunity for you to get involved at this point and start, you know, suggesting things that can be done. Now, I might get inspired to just add the second part of geopolymer on the end of this little session here, because it's pretty quick, but it would appear that my chemistry understanding is borne out by the facts of nature, and I'd possibly want to share that with you in a few minutes. So let's see how we get on. I'm just going to try and dig out this. Wherever I put it, I don't know. Oh dear. It's a problem when you have a million tabs up. Okay. Okay. Nearly there, maybe. Aye. Maybe you've got a link to it, Rob. Okay. Okay, so this is a blower. Maybe you'd want 4 of these things. These are 329 euros a piece. It does 1.9 Pascal air pressure performance, and it does airflow of 1,200 meters cubed per hour. But it's more these high pressure ones that they've got here. And there's a very nice one, I think by, it claims it's an Italian company. I saw something here, this C.I.C one. And this air blower here is the bit of the bee's knees. So there we go. It's got a big fat motor on it. And this has the capability of going from 0 pascals up to 65,000 pascals, or 9.427 psi. And you have a variation in the power requirement there from 0 kilowatts to 4.6 kilowatts. So using this device, you can get long run times. And firstly, the air is blown, so it's going to increase in temperature as it increases in pressure in the device. It doesn't start off being colder than ambient. So that's one thing. Plus, you can also pass this air through a heat exchanger and raise its temperature from whatever it is to a target temperature by varying the input power to the heat exchanger. So, and this has got like 600 meters cubed per hour of air in there. So it would be great if we could get one of these things and explore the pressure in there. It may not be appropriate, and maybe other things, you know. So I think that the flexibility here, you would be able to find, if it's within this range of 0 meters cubed per hour to 600 meters cubed per hour and 0 psi to 9.427 psi, if you could achieve the effect in that range, you would be able to find the exact psi that you would need, and then you would be able to find something that's better rated for the device. But Frank Polivka used a blower, and probably that is, you know, you should probably listen to the patent holder. So it's got a different armature here, one like that and one like that. Okay, so there's a range of different ones here, but I like this one because it's got, you know, it might not need the pressure, it might just need the cubic foot per hour, and these are things that need to be found out. But there's lots of different blowers that you can get. Okay, so having something that gives you a wide range over which you can explore the parameter space and hone in, you know, all the time you are having to adjust, or you've got like a 50-second window to do a test, it's going to be difficult, because in these systems it sometimes needs to get to a set of self-organization, a state of self-organization, and then at that point the effect may take a bit of time. So it's like you need to go and build the resonance, the energy needs to build up until it gets through a threshold, and then it starts being able to act. Obviously, in the case of a plasma situation, you've got a lot of ions in there, and the jet speed coming out of the Amasa gas nozzle is quite fast. Obviously, there's lots of ions because it's ignited. In Henk Jurien's, he's got plasma generally because of the high voltage potentials in there, and so on. And so, you know, there's a lot of things to think about, but I think we can solve a problem by not necessarily trying to invent a new wheel and use a blower. Is this the right blower? I don't know. People maybe need to think about that a little bit more. Okay, so I'm going to see if there's any questions, and then I'm going to probably do a quick addendum to the geopolymer before I call it a night. So David is saying, I wonder what would happen if you connected up an ion generator, high voltage supply with ionization into the inlet. So that's essentially what I was suggesting to Rob, and I would be very interested for doing that. Okay, so Rob is saying, I will be designing and calculating for blowers very soon. Excellent. Well, like I said to you earlier today, I'm sure people in the community would be willing to help support getting a blower if this is the right blower. If it's like a couple of €1,000 or €1,000 or whatever, I think it's money well spent, because you are breaking a lot of new ground here for the rest of us, Rob. And I'm sure it will be an easy sell once it works, but there's a lot of work to do before we get there. But already Rob has demonstrated that it can loft things, that the air is coming out at least in one place, similar to what you see in the Frank Polivka demonstrations. And it is doing some damage, not a lot of damage, but that the airflow rate that is going in at the moment, it's insufficient to loft an apple. And of course, it's being loaded from the bottom, and in several of the implementations of the Windhexe that we have witnessed, and in many of the commercial implementations, they're loading from the top, so it's going into the zone of the maximum airspeed. So rather than being loading from the bottom, but I think the loading from the bottom for me is the most interesting. So I'm glad that Rob has taken that path initially. So Rob says passive aggressive Windhexe, excellent. Okay, so right. Yeah, Rob, you do need a location for less temporary testing set up. I honestly think that it's small enough and can be spirited away enough that maybe when we meet up with Henk, Henk might be able to provide the space. The other guy that I'm coming with might be able to provide the funds for the blower. And I don't know how far you are from Schiphol kind of area, but the ability to go and test for a whole weekend with a blower and maybe a heat exchanger and everything working right, that might be a huge win for the community and for yourself on this. So yeah. Okay. You're pretty close. That's great. So we'll be coming into Schiphol on, I think, Thursday afternoon. So that's great. So Henk's near that area. So I think this might work very, very well. Great. And Henk probably has all the electronics to create a discharger. So, Bob, David's asking, were you able to figure out anything to retrieve Lion's apparatus materials? Yes, it's been funded by very kind donations, principally by Phil Power in New Zealand, who wrote the MFMP's Lena reaction calculator, and also from Jurien in Sweden, of Bobcat Sweden. So thank you to Bobcat Sweden also for making sure that happens. And I have one person in the community that's going to come down and help me organize what's going to be done. So there's a lot of things there that are the sort of detritus that you would collect through a life, which possibly isn't of any use to anyone. But I view this as the best thing we can give to his partner, who's not in a good way either, and it's meaningless to her, but she knew it meant a lot to Lion, and to make sure that nothing of value is lost. I'm really the community has come together fantastically for this, so thank you to everyone that the well-wishing, and I'll pass on those thoughts, and to the community for the support. It's really impressive, actually, what's happened. So thank you very, very much. Okay, so I'm going to do a little bit of an aside here before I close out, because I need to get ready. I've got to go to the airport at 200, so 0200, to get on the bus, and it's going to be an exhausting couple of days, the next few days, because of what needs to be done and the amount of driving that needs to be done to get it all sorted. But anyway, what I'm going to show you is, I was thinking, if, you know, my logic with the geopolymer stuff was that if you had a natural process, and we showed that the natural process of, how should we put this, of water coming out of the ground and from a volcanic source was able to do something with calcium carbonate. Whether it's synthesized in the reactor, it doesn't matter, but it's supersaturated. So since I observed that it was literally depositing hard limestone, therefore it must be something that you could replicate as a process. And remember, what we saw from these hot springs was that the calcium ions here are one of the highest numbers of ions in the ions, and in the anions you had this bicarbonate HCO3 and carbonate ions, but predominantly bicarbonate. And then down here you had free carbon dioxide. I think those are the most important things, as you will see. So I thought that there must be a building material, because people would have exploited these deposits that are formed from this kind of volcanic type process and this mineral water process. If the deposits are so hard, why wouldn't you use it? Well, it's a day or two ago, I looked into it and I thought, well, you know, this is what I'd have done if I'd have had a bit more time. I'd have done this in the original presentation. But here it is. It's called travertine, and it's basically, travertine is a form of terrestrial limestone deposited around mineral springs, especially hot springs. It often has a fibrous or concentric appearance and exists in white, tan, cream-coloured, and even rusty varieties. It is formed by a process of rapid precipitation of calcium carbonate, often at the mouth of the hot spring or in a limestone cave. In the latter, it can form stalactites, stalagmites, and other splitherms. It is frequently used in Italy and elsewhere as a building material. Similar but softer and extremely porous deposits formed from ambient temperature water are known as tufa. Okay, so travertine is a sedimentary rock formed by chemical precipitation of calcium carbonate minerals from fresh water, typically in springs, rivers, and lakes. That is, from surface and ground waters. In the broadest sense, travertine includes deposits in both hot and cold springs, including porous blah, 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 blah. Okay, so the reaction is this, my friends. The reaction is this. Calcium carbonate and water plus CO2. Oh, what does H2O and CO2 make? That makes carbonic acid. This is literally what I was saying, okay? Right? Carbonic acid takes calcium carbonate and it makes the Ca2 plus ions and the 2HCO minus 3. What do we have in our material here? We have an incredible amount of HCO3 and we have a large amount of Ca2+. And also we have a lot of free carbon dioxide, which means the water has as much carbon dioxide as it can possibly take, and there's still free carbon dioxide left over. Now, the carbon dioxide is being produced by the volcano. Is it literally being produced by the Lena process? Maybe that's occurring in the volcano. And what do we know? Carbon, triple alpha, and oxygen, quad alpha, are some of the most abundant elements that are synthesized in Lena. So why would you not get CO2 produced? And if you've got CO2 produced, and we know that calcium in Lena is one of the most abundantly produced elements, the two together make your calcium carbonate, don't they? Right, so that's what we have. Travertine is saying here. So the formation of travertine begins here when groundwater, H2O, containing an elevated concentration of dissolved carbon dioxide, CO2, comes into contact with limestone or other rock containing calcium carbonate. The dissolved carbon dioxide acts as a weak acid, carbonic acid, which dissolves some of the limestone as soluble calcium bicarbonate. Exactly what we saw in that spring. So the logic was, the spring is doing this. Everything we need to know is in the analysis of the spring water. And so it is. Okay, so this is a reversible reaction, meaning that as the concentration of dissolved calcium bicarbonate builds up, the calcium bicarbonate begins to revert to calcium carbonate, water, and carbon dioxide. So long as there is nowhere for the carbon dioxide to go, chemical equilibrium is reached, where dissolution of calcium carbonate is balanced by precipitation of calcium carbonate. In the groundwater moves into an environment with a lower concentration of carbon dioxide, as measured by its partial pressure, PCO2, some of the carbon dioxide will escape into the environment, disturbing the equilibrium and allowing net precipitation of calcium carbonate to take place. Ca2 plus 2 bicarbonate goes to calcium CaCO3. That's basically your calcium carbonate, your limestone, plus H2O plus CO2. So that explains exactly the process that is going on in this hot spring. So it may be the case that if we can get a Windhexe to smash up our limestone, okay, and again, what I was saying is it's at the grain size that was observed in some of these megalithic structures. Then you take a proportion of that and you put it to one side, and that is your aggregate. Now, what you want to do is, I suggested you might need to heat it to make it calcium oxide, and then add carbon dioxide to the water to make to make carbonic acid, and then mix the whole lot together. You get some slaked lime, some extra carbon dioxide in. It might just be that you need to make high strength carbon dioxide, high amounts of carbon dioxide in water. So carbonic acid plus a lot of extra carbon dioxide in there, but you need to keep the partial pressure on there so that it's got too much. It's got a lot of carbon dioxide on the outside. So how do you do that? Well, you create an environment around your rock which has got a lot of carbon dioxide until the point at which you want it to set. Then you would just expose it to the air. Anyway, I think somewhere along in this whole set of parameters we can come up with a solution. So what does it look like? Well, here it is in Turkey. This is a site, it's a World Heritage site, and you can see the size of the town here and this huge crescent of this wonderfully deposited travertine here. And here it is, and you can see these little folks up here. If I go and zoom into this, you can see this really is rather a large amount of travertine here. So let's have a look. These are people up here. They are people. So this is a large amount of travertine. Okay, so we go back there and we go forward again. These travertine ponds, very, very nice. Have you been there, Artifact? Lucky you. That's all calcium carbonate deposits. Yes. Okay. And here we go. It is again. Now, what did they do with this travertine? Well, they built buildings. Here is a World Heritage colonnaded street in Laodicea in Lycus. Okay. These are colonnades. These are pillars. Yeah. I think they're Doric pillars predominantly. And the street there made of this material. Here is another part of this place. Okay. And there's some people enjoying a bath. Now, what other famous buildings around the world have been built with travertine? I'll just give you a couple of examples, but this is not something that has not been used by ancient people. Firstly, the Colosseum in Rome. That's been around a while, and yes, that was made with travertine. Okay? St. Peter's Colonnade. Yes, in the Vatican, made with travertine. Okay? And then Sacré-Cœur in Paris. This has been made largely, or in quite a large part, by travertine. Okay? So travertine is something that is used. Okay? And there we go. So you can read all about travertine. I'll include these links in there. You can even make vessels here in travertine, and this is a very porous travertine in a and this is Europe's longest castle, is 1,000 years old, but built mainly with travertine. Burghausen Castle. Okay, that's the longest castle in Europe, is built with travertine. Okay, so what else do we have? So essentially, the chemistry in here pointed into a direction where you could make a geopolymer. And here we go. We got some considerations here. And this is quite nice because it talks about the hardness. Okay, and so it has a Mohs hardness. Where is it? It says here, 6 considerations when choosing between travertine and sandstone. We understand how picking between travertine and sandstone can often get confusing. The similarities of both stones, especially in the soft colour tones, make choice even more difficult. This blog post intends to list the differences and highlight the strengths. So, hardness and porosity. Well, sandstone is rather harder than travertine, falling between 6 and 7 on the Mohs scale, whereas travertine is 3 to 4. But travertine can be much more dense. Okay, so it can be polished to a higher degree, and sandstone is easy to carve because it's less dense. Okay, so they have their different uses, but you can see that if the Colosseum, St. Peter's Colonnade, the Sacré-Cœur, and these ancient buildings were all built with travertine, then possibly it's a good building material. Okay, and largely you can make it synthetic. So you can make them very, very nice looking slabs, and you can polish them. And what they do actually commercially is they seal them to prevent staining, because there's still some porosity. So in this case, you can get all these different colors of travertine here, depending on where it's come from and the impurities in there. Now, what I'm suggesting is that what it says actually here is the difference between travertine and other natural stones lies in the formation of the rock, the hardness of the stone, and its appearance. Travertine is formed in hot springs and or limestone caves. Travertine stone has holes within the stone which are caused by carbon dioxide evasion, making great for need for slip resistance areas like pools and patios. Travertine is comparable with marble in terms of hardness. It's comparable with marble. That's what I was saying. The marble that I have behind me, when I was feeling that, it felt at least as hard, what I now know to be travertine in that spring in Japan. Okay, so it's as good as marble, basically. Travertine is comparable with marble in terms of hardness, ranking 4 to 5 on the Mohs hardness scale. Travertine's subtle veining adds texture to space without adding too much attention. Okay, so the thing is that travertine can actually be several levels of density, and apparently you can have porosity down to just 2%. So very, very low porosity. So here, fresh travertines vary widely in their porosity, from about 10% to 70%. Ancient ones may have porosities as low as 2% due to the crystallization of secondary calcite in the original pore spaces, while some of the fresh aragonite travertine at Mammoth Hot Springs has porosity greater than 80%. So if you want really, really hard geopolymers, what you want to do is, in my view, start by mostly having calcium carbonate, right? And then you need a binding agent that then ends up as calcite. What is calcite? Calcite is just pure crystals of calcium carbonate. Okay? It's just the kind of like white stuff here. that you get in stalagmites. It's like this kind of stuff. It's pure, okay? So what you're wanting, therefore, is, in my view, these particles bound together with this other material. Can we achieve that by either producing calcium oxide and using the carbonated water in there, or does it just need a slurry of highly carbonized water with maybe carbon dioxide continuously bubbling through the entire thing as you're mixing that together with the aggregate, which is also calcium carbonate but unaffected, and then you have that whole lot, and maybe it starts to go in a little bit hard, and you put it into bags. You might put it in leather bags and just leave it to set for 6 months, leave it to set for a year. Who cares? Who cares? It could just sit there in a mold, sitting there for a long time. And there we go. So, like, this is what I'm thinking. Okay, so I will do another presentation that on carving. It's going to be in addition to the Seth side of things that I published earlier today, but I don't know when I'm going to get to that. I wanted to try and get it out the door today, but I haven't been able to do it. But there we go. So, to review, I'll go backwards. Travertine is a real thing. It makes real famous buildings all over the world, which have lasted for an extremely long time. And it is, in its finest sense, calcium carbonate with calcite filling the pores. Calcite is only calcium carbonate, as you can see here. And that is what I believe we want to target, to end up with something that is a geopolymer type calcium carbonate type rock. And if you're building a pyramid, you don't need to have it perfect, and you could probably just face it with natural material on the outside. So it doesn't, it kind of doesn't matter about the bulk of the pyramid being porous, because you want the hydrogen to go through it. It's not an issue. You just don't want it to come out on the outside. And this is what I'm saying, that the fine marble that was faced on the pyramid, I believe that was the seal. That was the seal to the hydrogen, if we are to believe that is what occurred. So going back to the start of today's presentations, we looked at the work of, if I can get there, it's going to let me do this. And we go here. So this was Windhexe Update 2, end of the 4th week in April 2023. And we have this hilt of a sword from Finland, which is from the 3rd or so century Anno Domini. And, of course, the sword coming down from the Windhexe is the bit that does the destruction, in my view. And so this is both a symbol of power and a tool of wielding power, or part of a tool of wielding power. And it's in exactly the right place. And then we looked at the work of Chris Scott with his Rankyosh Vortex, his pseudo mini Windhexe, injecting steam from a coffee maker, cappuccino steam, and novel experiment, seeing some interesting effects. Don't know whether it's real current or whether it's actually an interaction with a Hall effect, but other ways of investigating this will separate that out. But certainly there was a signal, and the signal got a lot stronger when there was steam injected into there. And it would appear to have drained his battery, done something a little bit weird there, which is interesting. That we get the reports of these people that have their batteries drained when they go into crop circles and these kind of things. And so very nice set of experiments there, Chris. Thank you very much. And then, oh, that's very loud, isn't it? And then Henk Jurien's interpretation of taking on the sacred geometry in this very simple experiment, which pops into his Vega experiment. And he's had some another additional things here with a magnet and supported that with some mica, and that consumed a chunk out of the side and going into the center of the aluminium foil cylinder block. And also we saw the marks of these plasmoids going around in an annular fashion around the magnets. Here in this test, he took out the magnets but just kept with the mica sheet and found that it bored a hole through the side, a little bit up from the bottom, and no real effect on the top or around most of the rest of the sides. But when you took out the dome from the top, it kind of like did a very different effect and kind of started to eat all over it. Okay, so really wonderful set of tests there. And then last up, the very excellent work of Tony Jabony, Acc, Robb in Holland also. And he showed the way with his Windhexe with a whole series of tests in his beautifully designed thing. I'm not going to run through the tests, but there was a whole bunch of them. And he recorded it in this PDF. Very detailed, excellent approach to doing this research. And you can see the tests listed here with what he did, at what time he did them, and so forth. And then how he ended up. And then a whole bunch of beautiful images here of the device being leveled and aligned to the cardinal points, and then various parameters of particulates and moisture and temperature in the air, how to do the measurement of the shim for setting the slit size and different slit size. That's the overall view of the device. This is a look at the top with the port adjuster on the top, how he's marking up things on there. That's particulates of this yeast left in the drum, the cone, and that is it. So those are what I had for you this evening in this review. Thank you very much for everyone involved. Really excellent. Another round of applause for the experimenters and their work over the last couple of weeks. Thank you very, very much, guys. Okay, so I'm going to see if you've got any questions there or relay something. Otherwise, I'm going to call it a night because I need to go and pack my bags. So Corky said there is a slip of cement in inverted commas between the Great Pyramid stones. Probably good. Yeah, probably this kind of thing, maybe. They would probably, if it was a geopolymer for the whole block, then they would put that in first, and then they would just fill the gap with the same kind of stuff and maybe slightly different mixture. Donald Best says, I will be doing a pyramid, but doubtful I will make it solid. Okay. The mica was just a thing to support the magnets, and then he thought, well, okay, you know, this had an interesting effect. What happens if I remove the magnets? Do I get the same kind of thing? And then what happens if I move the dome? And so you got the same kind of thing with the dome and the magnets and the dome, but not with the dome out of the way. But in each case, there was the mica. So Simon asked, do you have 3D printer? Well, I mean, actually, Holland is famous for the Maker bot. Like, I think it's the Maker bot. Like, the founder is Dutch there, and I think a couple of the other ones is Dutch. One of the most famous is also Czech. There are quite a few places where you can go and just pay someone to do a 3D print. In fact, I actually have paid someone to make a 3D print of the fractal torus structure, and I actually haven't sent them the model. And that was months ago. So I do actually need to get that printed because I've actually paid for it. So there's lots of places that you can get that done. So David Butlier's got to go. Thank you once again, everyone. I'm going to say good night. Dobro noc, buenas noches. I'll see you soon. It's really good fun, guys, and thank you again.